Okay, good afternoon, everyone. Thank you for attending today's webinar on the interconnection of energy and vapor, design of walls. Uh, this webinar is recorded. The recording is posted to the Code Adoption Toolkit. Give it like a week or two. Then they usually get it on there, or you can always check out Colorado Energy Office's YouTube page as well. It's posted on there. If there are any issues with audio, please write me in the chat. My name is Erica DeLello. I'm a senior project manager for Noresco. This series is sponsored by Colorado Energy Office with training materials created by Glenn Mathewson. So thank you, Glenn. So Glenn and I have been working to provide trainings just like this one. This is one webinar within the series. So we've got a whole bunch of other trainings on the docket for our Wednesday webinar series. And then we do also have, we're wrapping up our heat pump series as well on the 26th of March. So that one's at 8 a.m. And it has been included in our outreach. But if anyone's interested in attending, feel free to write me in the chat and I'll send you the link to register. We do also offer role-based trainings and tailor group training. So if for a role-based training, for example, it's a deeper dive into the energy code. It basically looks at the energy code through the eyes of the user of the code. So if you're a plans examiner, building inspector, an architect, engineer, contractor, we've got a training specific to your role as it relates to the energy code. So if you're interested in that, again, reach out to me. Happy to set something up for you guys. Let's see, and then we've got the Code Adoption Toolkit, which I've linked here. Sorry, that's should be shifted down a little bit, but there's a whole bunch of different great resources on the Code Adoption Toolkit, including significant changes, checklists that are comprehensive and can be tailored to your jurisdiction, different guides, and of course, all those previous recordings of trainings and whatnot. But one of my favorite resources is the Colorado Codes Helpline, and that helpline is an awesome resource. Glad I appreciate the enthusiasm. It is basically available to anyone in the state of Colorado. You can submit a question on any of the I codes or stretch codes, anything specific to Colorado. We're here to help. A subject matter expert like Glenn will get back to you in just a couple business days. So the QR code's on there. If you guys want to bookmark that, I highly recommend it. Okay, now I will pass it over to you, Glenn, to take it from here.
Great. Thank you so much, Erica.
Yeah.
All right, let's get the screen share going. And we'll pick that one. And a little moment. There we go. Okay. Oh, wait, let's move the poll. Okay. All right. Can everyone see the screen? Interconnection between water, air, and vapor in walls.
Looks good.
That is what we're going to do. And, you know, as I'm sitting here looking at this and thinking, I'm like, this isn't a long enough title because really, this also should include, you could call it energy or you could call it thermal, but obviously there's an energy part to this as well. As you can see in the slide here, we've got the energy code on one side and we've got the building code on the other side. And we've got a lot of different things that need to work together, water, air, and vapor control from the building code side in different parts of the code, well, air being energy code, I should say. But these are in different parts of the IRC, different chapters, different sections, and all really ultimately have different purposes. You know, for thermal control, for energy code, we're trying to handle one thing. And then for water and vapor control in the walls, we're trying to focus a little more on the building. So this is a tough subject to go over, and this will be kind of a little taste for you in this 1 hour webinar. This class started. I put this one together for the Colorado Building Science Symposium, first annual. Hopefully, you know, we'll see the hosts of that do that again every year. But it was, hey, you got an hour segment to try to cover this subject. But I have also developed this basically into a full day class that I've taught just recently at two events. And so coming back into this hour webinar is like, okay, we are going to be scratching the surface. Okay, I'm going to be introducing you to some things, getting your brain thinking about some of these things. And then, unfortunately, not unfortunately, but because of, 1 hour versus like a full day class, I won't be able to go as deep into these, in a presentation for you. But the goal still is that you get enough curiosity, you get enough information. I point you to a few sections. And then, of course, learning is an individual thing. You've got to be the champion of that and going out there with your curiosity and your questions and finding the answers. And so in all of my classes, whether it's a full day or a 1 hour, I always say I want you to leave with more questions than you got answers. Hopefully I hope you're going to get some answers or some information that's new to you. But as an educator, my goal is also to get you excited, get you interested, so then you lead in finding more information and more education for yourself. So that's kind of just a little, I guess that's my insecurity of like, man, there's going to be things I want to keep talking about that I'll have to move on to the next slide and then just let you guys be curious. So being, we have only a time here together. My name's Glenn Mathewson. This is kind of my big collage slide of my career to give you an idea of who I am, what I do, what my qualifications are. But in a nutshell, I started as a 19-year-old laborer here in Colorado at age 19, just sweeping houses for a home builder. And all of my construction experience and code experience has been here in Colorado in terms of, in the field, on site as an inspector. And now, many, many years later, from that young 19-year-old self of mine, I am just an independent building code educator and consultant, always trying to get a positive and proactive message about code out to everybody. That's why I was cheering on the Colorado Code Helpline, because it's for everybody, right? And code is something that if anyone's involved in construction or doing construction, I want to welcome them to being a part of learning this, not just the regulators. So it's my hope that we've got some mixed audience here today. But regardless, I'm happy there is an audience today and some folks to share with. If you want to learn more about me, you can go to glennmathewson.com. But that's enough of that. So, like I said, this is a very slimmed down. We could do a full 8 hours on vapor control and on all these interactions in walls, ceilings, floors. So we're gonna see what we can touch on in these next 51 minutes here. And in a lot of my classes, it sounds elementary, but I always often start at the definitions. And that could be elementary for the new folks that are in the industry. Yes, these are elementary baseline things to learn and understand the importance of chapter 2 of all the I codes for definitions. But even for you senior folks that have been, doing this longer than I've been an adult, well, guess what? You're also not too experienced or too wise, or you've been doing it so long that you don't have to step back sometimes and understand terminology. So I have a specific reason to talk about these definitions because they are things that have changed over the long history of vapor control. As a code historian, I mean, vapor control, we can go back to the 1927 Uniform Building Code, and we've got discussions on ventilation of crawl spaces for vapor management and to reduce condensation. So the subject is very old, which means there's a lot of things stuck in people's heads. You know how sometimes you learn something and it's hard to unlearn it? Well, the code is always relearning every 3 years, right? With every new hearing and every new edition. And so that's why I picked these. So weather resistant barrier is a term you'll hear used very commonly because it was a term we used in the past. But I'll show you the details of this is the term we really want to use today, and this is the term the modern code IRC is using now, a water resistive barrier. And then I'm also going to touch on the vapor barrier. Vapor barrier is sort of a dated term in code. But if you're just talking to other folks, building science, HVAC design, folks out there that aren't just buried in the code, like everything I do is going to be in a code, in the lane of code. And then from there, reach out to the other, to the science and to the design kind of stuff. So you're still going to see vapor barrier very much used by absolutely reputable, qualified professionals because they're not just held to talking the way the code talks. And I'll do a little explaining about how the term vapor barrier and where that does kind of translate to code. But in code, we use the term vapor retarder. Now it's a little more accurate, if you will. Even a plastic sheeting poly vapor retarder isn't a complete barrier to vapor. Like barrier sends that message that it's not no water vapor is diffusing through this material. And I mean, you could almost reserve that for glass, for windows. Glass is essentially just about a true barrier. So this is what we're going to do. We're going to understand why these changed from one to the other and some of the historical significance to that. I always love to pull a little history into these classes because the better we understand history, the better we understand today, and the better we can shape the future. Because in the future, today is going to be history, right? All right, enough of that. Weather resistant, water resistant barrier. Let's start there. And codes have been around hundreds of years. So in the long timeline of code, this is something relatively new. In the 2006 IRC, we got the definition for a water resistive barrier. And you can read that on your own while I'm talking. But of course, right, you can hop into chapter 2 after this is over and read a lot of this for yourself. I always encourage you, any of the code that I bring up, write down a quick section number or something and go read it later on your own. I don't do a ton of just reading you the code, even when I bring you up the language like this. So here we see the section related to water resistant barriers. And this is what we're going to find in the 2021 IRC. This was actually, there was some significant revisions to this section for the 2021 IRC. And so you get lots of details up here about how to install it and some other references. Again, read those things on your own. You're all professionals on this line, most likely. What I want to talk about here, we got these 4 different options. And the code is full of choices and options. That's something that when the public doesn't dig in and learn the code for themselves, they love to use that line, the code is the worst you can build and still be legal. And as someone that truly understands the IRC, for example, I find that to be somewhat of an ignorant statement, like not really just not knowing the code. Because if the code is the worst you can build and still be legal, my question is, well, which of these 4 choices that the code user can make, I mean, which one of those is the worst, right? So it just kind of doesn't make sense. The code gives lots of options and choices to those that choose to see the opportunity that it provides. So the first choice on here that I want to talk about is number 15, felt, because this is what I guess I would kind of say the prescriptive method. This is the cookbook method. This is the simplified recipe to just build a house for your family or to sell to another family. That's a material that you can buy at your, most lumber yards or home improvement stores or construction suppliers across the country. And that's also the very much a historical product as well. And then we get into the other options. I'll talk about those in just a minute. So number 15, felt water resistive barrier, right? I said this is kind of the historical product. So let's go back and look at this document I have that was published by a few different agencies and departments of the federal government back in 1950. And I mean, look at the title of this book, Condensation Control in Dwelling Construction. Sometimes when you talk about building science and vapor management and vapor control and all this energy code stuff, it's gotten a lot of attention over the last decade, 2 decades. But it's not new. I mean, we've been, look, here's a book about that subject, controlling condensation from back in the 50s. But however, just because the information was there and the research was put together doesn't mean that information was has been out to all the people and has become a mainstream understanding, which is why here today in 2025, I use this as a reference to kind of point back to a little bit. So here's a section on sheathing paper, right? And this is, your felt paper, your tar paper, your water resistive barrier, as we would call it today. And I like this little statement. It gives us a lot of clues about how this was functioning for us in the past before all of these new technological advances in construction materials, all the polymer based materials. And I mean, every day there could be a new material coming out that's very proprietary, based on chemicals and testing and interlacing of atoms and stuff way above my head. And how are we affecting things without realizing we're affecting things? And that's helps us if we understand, well, how were things before all these new products we have? So you've maybe, as I'm sitting here rambling on, you've already read this statement. Sheathing paper, sometimes called breathing paper, between the sheathing and the finished siding has been customarily used to reduce infiltration of cold air. Hey, that sounds like what? An air barrier, right? And to prevent the penetration of wind-driven rain. Hey, rain, like, the weather. So we can see how in the past, this sheathing paper, we were sort of relying on to do quite a few different things than just today, where we kind of focus on just the water resistive barrier. And we have all these other methods of creating our air barriers. But, here we see 1950s. Yeah, we didn't want leaky homes either, right? We didn't want homes leaking air, but we wanted them breathable with breathing paper. And that's one of the things that another point I'll try to get off in this class is so many people compare a house, an airtight construction for a house, and they say, oh my gosh, that's horrible. This can't be so tight. A house needs to breathe. And they're relating the house to a living organism, right? Like a human being breathing. How do we breathe? We breathe air, right? But isn't that kind of a bad comparison to compare a house, a shelter for a living organism, and then try to compare that terminology to the living organism itself? So, as we're going to see here in a little bit, I don't think that's a good comparison. Here we can see breathing paper more speaking to like this. This was a typical cheap white undershirt that you would typically use under, a nicer shirt. So when this Fruit of the Loom t-shirt here says breathable, do you think it's saying go out and, if you wear this outside in the wind, be careful because wind is going to blow through it? Is that really the message it's trying to tell us? No, it's trying to tell us it's breathable. It will allow water vapor to diffuse through it, and it will allow our sweaty bodies to dry via water diffusion, vapor diffusion, as opposed to air movement. So my goal to drive into you guys today is, yes, a house needs to breathe, and it can be as airtight as you want it, because a house doesn't breathe the way a human breathes, right? So here we have 1950s, put on your weather resistant barrier. It's going to do all these things for us: prevent wind driven rain, act as an air barrier. And then as we get through the evolution of code, we can find kind of a strange one in the 2000 IRC in the section on siding. And suddenly it tells us now no sheathing paper is required. And there's a various number of sidings here where it'll tell us no sheathing paper required at all. When I jumped into construction in the late 90s and moved on to framing homes and doing work for the home builder, we were putting homes in Arvada. We were building homes with OSB sheathing, and we just put the window right over that piece of Z metal flashing on the top, and then put masonite siding or directly over the OSB. No water resistive barrier, no sheathing paper at all. And I always remind folks that the 2000 IRC is a very, very unique IRC of all the other ones. This IRC was created by the combination of existing codes already. 3 existing code organizations that were saying, hey, we're merging into one. Let's merge all of our ideas and all this history and all the ways that we've been doing things. And let's compromise and argue and discuss and collaborate and put this together into one IRC. But then after that point, we went into the typical hearing process, and everyone writing can write proposals for it, and we go through the hearings. So there's a lot of things in the 2000 IRC that are strange, and then in the next couple editions they changed out. As you can see, 20 in the 2006 I showed you, we got the definition for water resistive barrier, and that's also the edition when no, you've got to put that on in all applications, other than, of course, there's always some minor exceptions. So in an interactive class where I do more interaction with the audience, I don't really try to do that too much in webinars. I just feel like we don't have the time, nor is it as convenient when we're all in person in a class. But if we were in person, I would ask you now, which one of these do you think it came from? Which of these code organizations was the one that was allowing construction with no sheathing paper, and in the argument of bringing it together for the code, they won? Well, hopefully you got your thought. I'm going to give you the answer. It's the Southern Building Code, the 1994 Building Code from the Southern Standard or Southern Building Code Congress International. Did not require anything, any water weather resistant barrier sheathing paper over OSB. So we got some ideas now of what that sheathing paper was doing for us in the past, but nowadays we have lots of other ways people are doing water resistant barriers. Number two here, that's for window and door assemblies. Obviously, we don't put tar paper over a window or door. So this ASTM test where my mouse is pointing to here is about water penetration testing of fenestration, windows and doors. So that would be a portion of the envelope that would not need to be that would count as a water resistive barrier. And then item 3 here is for exterior insulation finishing systems. And so those have water resistive barriers built into those complete systems that are tested as a system. And so those are 3, direct, if you will, like cookbook methods to do this. Here are your options. Use this ingredient, or use this ingredient. And then, of course, item 4. And what does item 4 say? It says, what other ideas do you have? Like, we're open. The code is not trying to just prohibit everything unless you do it one way or no other way. The code is trying to offer us ways that will work, but then always leaving it open to say, hey, got any other ideas? Got any new technologies? So many of you are probably familiar with the system or have seen it before. This one I have in the image here. And this is a water resist, or this is an OSB, a wood structural panel sheathing that has the water resistive barrier built into this proprietary product. And so what does this tell us? Other approved materials. And approved, hey, that's a very important word, right? Who gets to approve what? Does that mean it's based on a testing criteria? Well, what's the test method here? We don't have an ASTM test or anything shown. Well, approved is acceptable to the building official. And so what this means is, the way I like to present this is basically like a now hiring sign. The code is essentially saying, hey, currently on staff here, we have number 15 felt, we have windows and doors, and we have EFIS systems. And they're all performing the job wonderfully for us to provide a water resistive barrier. But we're always looking for new staff members to join our team, right? Now hiring. But what are we going to do if we were hiring a new staff to the building department team or to your design firm? You would want to find out what their qualifications are. You would say, hey, can you provide me your resume? Right? So the building official would want, what would make it acceptable? Well, show me your qualifications. Show me your test information. Do we have a standardized ASTM test? Is it referenced in the code? Is it not? Do you have alternative tests like through ICCES or through other providers of code compliance testing and reporting? And so then the public can show you that resume that they're qualified. This other way of doing it is qualified to do the job. And now as the building official, you can say, yes, you can join our team for this project and go ahead and you're a water resistant barrier. And then in doing so, hold on, there's other stuff we might want to think about, right? The felt paper, well, that was conventionally an air barrier as well, right? Would keep infiltration of cold air. So it might be a good time to go, all right, what other features, how is this alternative functioning in these other applications that the standard materials have been functioning for us since the 50s or before. So is this material an air barrier? Yes, no, that's for you to find out in reviewing the resume and how that then plays in with the whole design of the exterior wall assembly. And what about breathing paper, right? If suddenly we're shifting from using a 15-pound felt that is a breathing paper allowing moisture to water vapor to pass through, are we going to be doing something? Are we going to create any negative effect if we replace it with this other product, this other material? So it might be good for the designer to find that out, to ask the question, hey, how is this affecting air movement? How is this affecting vapor diffusion? All right, so there's some little tidbits on the weather resistive barrier to the water resistive barrier and how, what other functions might it be providing or could provide. Next up, we have the vapor barrier, now vapor retarder. And like I said, from 1950s, you can see here, and that was the term vapor barrier, vapor barrier, vapor barrier. And that's still a term used today in a lot of non-code professional conversations and professional documentation. And that's okay. But in the code, we don't use this term anymore. So let's talk a little bit about vapor barriers, vapor retarders, vapor diffusion, in a very quick little nutshell here. So there's this website I have found, dpcalc.org, but you can find lots of websites that'll provide little dew point calculators. This is just a very simple dew point calculator. 68-degree air temperature, that's the temperature of the air. I set it at 68 degrees because that is the minimum required heating for habitable spaces since like the 1992 code. So that kind of gives us a code-based example temperature, right? We've got to at least heat the home inside to 68 degrees. And then you can set the slider here for the relative humidity, and I set it at 45%. And I got that from the ASHRAE Handbook of Fundamentals, and they have this chart that they've adapted from some health and medical science and documentation. And these folks, much, in a whole different lane than me with code, have said to us, hey, look, if it's too dry or too humid, you create worse environments for all of these things that we don't want to live in, these environments that aren't so good for the occupants. And so if you look at their range of the optimum zone, very center of that is 45% relative humidity. So that's why I've used that over here in this slider. And what that results in is a dew point temperature of 45 degrees, saying if 68-degree air at 45% relative humidity touches a surface that's 45 degrees or colder, it's going to now be 100% relative humidity. We're going to make that air colder. The air can't hold the same amount of water anymore, and we're going to get condensation, which is not what we want. We don't want liquid water forming inside of our assemblies or absorbing into our wood materials inside our assemblies. So if we look at an old-fashioned, just typical wall dating back to the 50s, you got some gyp board on the inside, you got some sheathing on the outside, and these are just example numbers. 68 degrees inside. It's more. We have more relative humidity inside than we do outside. Outside it's cold and it's drier, and the colder air can't hold as much humidity either. And so we can see we have this temperature gradient through the wall. One side of the wall is 68, the other side is 30. This doesn't just happen in some, single magical point. This is a gradient of those temperatures. As you move through that wall assembly, you're getting colder and colder and colder as you go to the outside of that assembly. So here we have, no vapor retarder on this. We're having vapor diffusion pressing up against this wall, and it's going to pass right through that material. Lots of humidity. We didn't have any vapor retarders or barriers. And so now if we look in here, all right, we've cooled down the air. So I picked the number, say 56 degrees. We've also, colder air won't hold as much relative humidity. So that means we would actually have more relative humidity of the air. But, we probably did block or slow down some diffusion through here. So I've kept it at 45 just to keep this simple. But we can see how the colder air has lowered that dew point temperature, okay, down to 35 degrees. But look, we're right on the other side of the sheathing. So chances are we don't have enough insulation to keep that surface above 35 degrees. And remember, these values and numbers here are just anecdotal. I'm not the vapor scientist, I'm the code guy. So I can get away with just using sort of example values so we can get a basic understanding of this to understand how the code works. So here we're going to have humidity coming in, it's going to hit that cold surface, and 56-degree temperature, 45% relative humidity. Sorry, I forgot I had those clicked in the slide. 35 degrees, and this is going to lead us to condensation, right? This is what we didn't want. And so this is why we see, all right, vapor retarders, right? Back in the 1950s, put a vapor retarder or vapor barrier on the inside wall. Now we're going to slow that movement, that diffusion of humidity through here. And so what does that do? It lowers our relative humidity inside the wall. We haven't let all of that humidity come in as quickly, so we have less relative humidity. This means we can now tolerate a colder surface. And that's a good thing, right? Because if that humidity hits those cold surfaces inside of our walls, we're going to get the condensation. So now we can tolerate a colder temperature. And look, it's not that cold. It's 35 degrees. So great. No more condensation, right? We controlled the condensation. And that was working in the 1950s because look, there's not much other stuff to this wall, is there? There's no continuous insulation, there's no spray foam, all these things that change these properties of permeability compared to what we were used to with the quote breathing paper. So we can come in here, we can see now in the 2021 IRC, we've got vapor retarder classes, and we've got 3 classes of vapor retarders. And I'll take you through and show those in visual form in just a minute. But I want to point out an important thing here. Anytime the code refers to a class of vapor retarder, class 1, class 2, class 3, that immediately tells us that the perm rating, the permeability of those materials within these ranges was determined using the dry cup method of ASTM, ASTM E96. There's a dry cup method where it's testing the material in a more dry environment, testing it going from a 50% humidity to a 0% humidity, and then moving through the tested material. And we'll see here in just a little bit, there's also a wet cup method. And that tests material when it's more in a more wet environment, moving from 100% humidity down to a 50% humidity. And like I said, I'll say that I got another slide to get into some details there. So this is when I bring up one of my little, what I call bumper sticker sayings, my little quotes in code. And one of the things one of my sayings is, test standards support freedom. So back in the old day, it would tell us exactly what you needed to use. It would say, use 15-pound felt, use a poly vapor retarder, a plastic-based vapor retarder, things like that, giving you only one choice of material. And that doesn't really promote much freedom, right? But a test standard says, hey, go be innovative, go be creative, new technologies, new materials, new ideas, test them out according to this standardized test. And if they can provide the perm ratings between these ranges, then guess what? The code says you're hired. Come on board and do the job for us. And I say this is my bumper sticker saying, but honestly, I'm not the only one that does this. I was at this hot rod convention where people were bringing all their sports cars, and I couldn't help but notice someone had that bumper sticker on their sports car. And I was like, rad, cool. I'm going to pretend you all laughed at my silly joke because I still try to squeeze them in even when I can't see any of your smiling, laughing faces. But keeping it light, right? So here's what we get now, though, in the 2021 IRC. We can see that we have more options in there. Class 1, Class 2, Class 3. And look, there's lots of stuff listed like sheet polyethylene or non-perforated aluminum foil, fiberglass bats, vapor retarder paint. So it's still giving us like an easy recipe, right? Like remember, we're trying to build a basic home. It's just like a cookbook making green bean casserole. Let's just follow the recipe. It tells us buy some of these materials. But hey, remember, what does this say? Or other approved materials, other approved materials, other approved materials. Remember that now hiring sign? Now, in this sense, for the acceptable to the building official, you're given a little help, right? It's here on the license plate. How would you approve other materials? How would you review their resume? You would say, let me see the results of your ASTM E96 testing. Let me see that you've got, your material listed to that, and that you comply with that testing, and that's how you derived your different permeabilities, perm ratings to get your class. Okay, so yay, test standards allow for more innovation. And that's something, test standards promote freedom. Most people would think I'm crazy because it just sounds like another rule, doesn't it? Well, sometimes it's important not to just look at rules as restrictions, but see if sometimes these rules actually open us up to other avenues. So these are my little easy to remember ways, terms to remember these different classes of vapor retarder. A class one vapor retarder is going to be point 0.1 perm or less, like poly, right? Your sheet polyethylene. That's the classic vapor barrier. And this is where you're still going to hear folks out there outside of just the code lane, and they're going to be referring to vapor barrier. And that generally now is going to be speaking to a class one vapor retarder, vapor barrier. But remember, by the code, it's just a class one vapor retarder. So poly, that's an easy thing to remember, but never forget the now hiring sign. And then our class two vapor retarder is greater than zero point 0.1 perms up to 1 perm. And just an easy thing to remember is paper, right? Poly and paper, easy to put together. But of course, the now hiring sign, never forget that. In the 2006 IRC, here's where we have another thing to clue you into why there's a lot of disconnect. A lot of people have different opinions and different understandings of vapor control, and it has so much to do with this history and how these things have evolved. So if we were to go back to the 2000 IRC, we wouldn't have three classes of vapor retarder. We would just have one definition, vapor retarder. And in that code, a vapor retarder, or someone might have called it a vapor barrier, it was 1 perm or less. And that means, look, that means it included class one and class two back in the 2000 code. So where we've evolved in this and getting more specific is we've now broken apart just vapor retarder as being 1 perm or less, and we've broken that into two separate categories. So now we can look at poly and paper separately. And then this one doesn't tell us, in 2000, was it a dry method? Was it a wet method? Well, that doesn't help us a lot, especially with the movement and the much more specification we have now on this subject in the modern code. So we can see in 2003, just a quick note, the definition changed again. And this is where we now see the reference to the desiccant method, which is also the dry method or procedure A. There's a few different terms that are used for that. Dry cup, dry method, desiccant, procedure A. And so 1 perm or less. And now we can trace this history all the way back to that 1950s book. Because what does it tell us here, right? A good vapor barrier should permit, as tested, right, under laboratory standards. Now we have a reference for that test, ASTM E96. Not more than 1 grain of water over 1 square foot of material in 1 hour of time by a dry method. So, right, in this time, and this might be in a lot of people's brains still, a vapor barrier, 1 perm, well, that would be equivalent to class one and class two vapor retarders today. Now for the biggie. The big change with this is recognizing paint as a vapor retarder. Paint, just a simple term. There could be other materials constructed to do a class three vapor retarder, but I try to keep it easy, right? Poly, paper, paint, right? So a nice summary to help you understand class one, class two, and class three. A class three vapor retarder, paint, that's going to be greater than 1 perm and then up to 10 perms. Now, here's where I feel like I have to point you to this definition in the IRC. It's been in there since 2000, and it's about what does it mean to be vapor permeable? And here we see vapor permeable means 5 perms or more, and that's tested under procedure A or procedure B. Now, in my bigger class, I can go into explaining to you that The IRC is Frankenstein. I'm just going to do this real quick for you, but the IRC is Frankenstein's monster. It's been put together by parts and pieces of different people over different periods of time. We have stuff in the IRC from people living in the 1927s before my father was even born. And parts of those people are still in this Frankenstein's monster of our IRC. So what I can kind of tell you in what I've discovered through my research is this really does not have any real relevance to vapor management in our building assemblies at all. This is kind of a dated definition in terms of its use in understanding parts of the code. When you get to appendix chapters, like for straw clay construction and hemp line construction, you'll see a lot more discussion of vapor permeability in those appendix. But those are new just in the last few editions, and this is something that's been in there a while. But something to keep in mind, right? If it's 5 perms or more, we're definitely seeing it as vapor permeable, even though between 5 and 10 perms, we're still calling it a vapor retarder. You see how it's kind of hard to teach that without explaining that, you know, the code's not perfect. Anyway, so paint really is getting us to this idea of being breathable, being able to dry. And whether this is the right slide to explain it or not, I'll make sure I get it out in the air. When we're looking at the dry cup method, the classes of vapor retarder, class 1, class 2, class 3, under dry cup, and being 1 perm or less, class 1 and class 2, we're primarily focused, the goal there is really to keep that water vapor from diffusing into our assemblies. But then we might want the water vapor to be able to move out of our assemblies and dry out, right? Just like if you're wearing a few too many clothes and you get hot and sweaty, you want those clothes to let you dry out. So the idea of paint is really pushing us towards this idea of drying, of getting back to being breathable. So this is a Google image of searching a term. I love searching with images because it gives you a taste of what the general public is talking about certain terms. And there's this term that was coined not too long ago, a smart vapor retarder. And so smart vapor retarder, well, that was the term coined by the public and in sort of creating this concept. And someone said, well, let's get that recognized in the code. So you'll see something coming in our 2024 edition of the IRC, a term called responsive vapor retarder. And again, I encourage you to go read these definitions. You can read all the ICOs for free at codes.iccsafe.org. So even if you don't have a paper copy or your own PDF of this, you can go read it online. But this basically tells us, all right, a responsive vapor retarder means it's a class 1 or class 2 vapor retarder. And that automatically, just by that, we already know, okay, that means it's under the dry cup test in a dry environment from 50% humidity moving into 0% humidity. But then what it says is that particular material, a responsive vapor retarder material, when tested under the wet cup, is actually 1 perm or greater. Now, I simplified it by saying, it's a 1 or 2 under the dry cup, and it becomes a class 3 under the wet cup. But that's just simplified, because remember, class 3 goes up to 10 perms. But if it's a responsive vapor retarder, we don't care how much it opens up to. Ideally, it opens up to as many perms as you could possibly get. So this is an important new movement we're seeing in this vapor control design. All right, and that speaks us back to that breathing paper, right? Sheathing paper, often called breathing paper. If we look up the material properties of this material, we'll find that breathing paper is dry cup, it's 5 perms. Hey, isn't that the definition for vapor permeable? Even in a dry cup example. But then in a wet cup example, hey, we got a leak into the wall, or somehow we got condensation in there. Now we got this wetness in the wall. That's going to open this material up even more under humid conditions, upwards of 30 perms. Just quick note, I found that information at buildingscience.com. That's a very, very reputable site with building scientists there that are world renowned. So again, I'm not going to point you to a site that's, Billy Bob's backyard building science. I mean, unless Billy Bob's, got some serious reputation behind him. So this is something you can search online. I find it to be very useful because I am not an expert in material properties, right? But that's part of understanding code. So I'll utilize this as well as some other sources to help me understand our values and permeability of different conventional construction materials. So breathing paper, right? Back to this. Here it tells us, 5 grains or more in the 1950s is what should be a satisfactory breathing paper. Doesn't that correlate with 5 perms for permeability that I just showed you in that definition? So we see that this new stuff in the code isn't really all that new. It might just be new for the code. So this is my favorite way to kind of break down all these different control layers for the house. I mean, it's Colorado, right? So we got snowboarders like me, and then we got some of you dorks out there that ski, but whatever. I'll still bring you into the fold. We're still snow riders. That's cool. What do we have here? We have a shell, bib pants to wear. And so what do we get? Waterproof, right? We don't, so it's going to be slushy spring riding soon, and we don't want all that wet melting snow to get our clothes wet and our bodies wet. So we have a waterproof shell. That's our water resistive barrier. But remember, it's springtime. We're getting hot and sweaty underneath this stuff too, right? So we want that to be a breathable fabric, right? That doesn't mean it's air movement. That means it's vapor permeable. But then sometimes you're really hot, right? And just drying through the fabric's not enough. So we really want to ventilate. We want to open some windows and really just let that cool air come through and ventilate out the house, right? Or ventilate out our bodies. So we have, these clothes have venting zippers, and these venting zippers are often in our most humid locations, right? And I can relate that to where do we see exhaust, additional openings for ventilation or exhaust for ventilation, kitchens and bathrooms, kind of like our armpits and our crotches, right? I mean, sorry for the TMI, but it fits, right? The shell of our homes are for shelling a human body, just like our clothes are. And so these are put in wise locations, just like exhaust in kitchens and bathrooms or windows. And then, wear resistant fabric, right? We're gonna maybe on our knees a lot. We're getting physical damage against physical impacts and physical scraping of crusty, icy snow where we might fall on our knees. And that would replicate, right, our cladding, because the water resistive barrier is kind of protected first behind this physical protection of our cladding. So all of that is IRC. All of this, you're going to buy this part of your snowboarding or skiing outfit out of the IRC store. And you can make lots of different choices in how you want to do this. But you might now want to be warm, right? As a human being, it's cold up there. You want to be warm, so you want thermal insulation. And that may be a different layer. That's how I do it. So I can adjust and adapt my shell, but I can also adjust and adapt how much thermal insulation do I need based on climate zone, right? Is it deep in January and it's just cold up there on the mountains? Or is it warmer later? So we can even compare that to kind of climate zones where we would change the thicknesses and the level of our thermal insulation. This is the energy code over here. And this is what folks need to realize is just as you can buy 2 different pieces for this, you also need to make sure they work together, right? If your shell's too small, you may not be able to put a thick enough thermal insulation underneath. So just the same way when we're doing our envelope design, choices you make in vapor control, it's up to the designer to be sure that those mesh with choices that are made for thermal comfort and for energy code. And then just to wrap this up for fun, right? Venting zippers you have to open by hand. Like a window, you have to willingly open to ventilate. But what are we moving to now in our control of our environments, right? Mechanical ventilation, whole house mechanical ventilation. So that would be like this funny jacket I found online is a jacket that has fans built into it, right? So you don't have to open your windows or your zippers. You have the mechanical ventilation in there. Oh, so clever. Okay, so let's see about this disconnection. It's been around forever. This is a book I have from the 1940s, and inside this book, there's 3 sections. Now it talks about in this book from the 1940s, vapor permeability of materials. And where do you find that? Well, obviously in the materials chapter, telling us about the properties of materials. But in this 1940s books, it also talks about thermal values of insulation materials, R values, U factors of insulation materials. And you might think we'd find that in materials, but we don't. We find that in the occupancy part of the chapter. Why? Because that's what we relate. We relate our thermal underwear, our insulation. That's all about us, right? That's about us, comfort and cash, the occupancy from the human being. They're not worried about the condensation happening inside the wall. That doesn't get the forefront attention. And so we see that the same way in the IRC, right? All of our vapor control stuff comes out of the other chapters of the IRC. Actually, I'll do a slide for that in a second. Um, Thermal comfort, thermal control, R value, still an occupancy focus, right? That's really how you're going to sell the house to the new home buyer. How great this is for your energy bills. No builder's going to say, "Oh, this house is amazing because it manages vapor inside your assemblies." That doesn't get you your house sold. It, didn't back in the day and probably wouldn't today. So we see this as the energy code part, and that's embedded into chapter 11 of the IRC. For permeability and for vapor control inside the assemblies, well, occupants don't care about that. Where's that located? We're going to find that in chapter 4 for the crawl space areas, chapter 5 for slab on grade concrete or wood floors on grade. That we're going to get chapter 5 for that. We're going to have to go to chapter 7 to talk about vapor barriers, vapor diffusion, vapor control in chapter for walls. That's going to be chapter 7. And then if we want to talk about it for roof or floor, roof ceiling assemblies or attic assemblies, now we're jumping into chapter 8. So now let's talk about air leakage a little bit. Oh, what is air leakage doing for us? Well, air leakage is moving water vapor. Blat, nobody cares. All right, what else is air moving? Air's moving heat, right? It's leaking heat. And now we got the attention of everybody, right? Comfort and cash. And so we see all that focus on insulating the building. But what does all this insulation, how is that actually affecting our vapor control? And I'm short on time. Like I say, I obviously have a hard time with these 60-minute things. I'll keep working on that. So real quick through, I'll just talk about air leakage. Has been a discussion back from 1992 for the American Society of Heating and Ventilating Engineers. We had it in the model energy code before we had the international energy code. Air leakage is an old subject, over 100 years old. And of course, we have it in the IRC starting off with that 2000 edition. So energy code telling us air barriers. But in that 2000 edition, we also had these other chapters. This was in chapter 3 at the time, saying all of the assemblies, floors, walls, ceilings must have a vapor retarder. And the exception to that was if they're ventilated. So we could get away from a vapor retarder for the attic because we could ventilate attics. We can ventilate our crawl spaces, so we could get away from vapor retarders there. But what about wall assemblies? Well, we've never historically ever, conventional construction doesn't ventilate the wall assemblies inside. So we would have mandatory vapor retarders, right? And that was class 1 or class 2 at that time. And it told us to put that on the warm in winter side. Okay, warm in winter side, vapor retarders in all walls. Well, what was the goal of that, right? We got this uniform vapor load pushing against the wall. We're going to reduce the diffusion coming through. But let's say we have an electrical box right here or something, or a gap or a hole, something cut in our vapor retarder. Well, at that little spot right there, it's going to not restrict vapor diffusion. You're going to get all that water vapor moving in. But as you can see, the rest of that wall area, it did its job. It did slow down the vapor diffusion and act as a vapor retarder. And this is where I bring up kind of a strange analogy that maybe will work for some of you. You've probably been to other classes and other presenters bring this up a different way. But I kind of see this floor and look at this. We got a floor and we've got a floor drain. So the floor represents all that vapor retarder, a nice big sheet of poly, real easy to put up, and it's going to work. Except we got the cuts around the electrical box right here. And so, we have a little breach in our vapor retarder. Well, let's look at this sand and let's consider this sand The air and vapor diffusion of the air. Well, this sand sitting on the floor is putting a uniform load pressing against this floor in all parts. Well, any of the parts that the sand or water vapor is pushing against the floor, it's being retarded. But in the part where the gap is, that's where that is not going to have a vapor retarder, and our vapor diffusion is going to move much more rapidly through that. Okay, so the point is, it's pretty easy to put up an effective vapor retarder. It's going to work everywhere that you just roll that sheet, and it won't work just at the little leaks, but it's only going to let the part right over the leaky part. It's only going to allow the vapor diffusion in that spot to move through. So if we switch this over now and talk about air leakage, because air is also moving vapor with it. We test our air leakage in our homes. Energy code requires blower door tests and limiting our air changes per hour. But this is from one side of the assembly to the other side of the assembly. And we can see back in the day, in the 2000, this section also told us air leakage through the building thermal envelope, right? One side to the other, because it's all about our comfort, right? Energy code means I'm more warm and my energy bills are low. So that's not focusing on like what's happening in the assembly. So we get, okay, we got our water resistant barrier, say on the outside, and it's functioning like an air barrier, and it's limiting that cold air coming through. Or maybe you've put now in modern times, you've put a type of proprietary sheet good or something else that's sealed up. So you get your big time air barrier there, and you're going to pass your blower door test. But now we still have that vapor retarder and we have that hole. And now we have air pressure inside pushing up against this wall. And of course, the air is going to move right through where the hole is. But here's where it's going to act differently than vapor diffusion. All the rest of that air is also going to move through the hole. It's not going to be blocked by the air, by the vapor retarder or by the drywall in the same way the water vapor would be blocked. And so we're going to get a ton of that humid air to be able to all come through that hole, illustratively. And so going back to my floor drain example, now let's look at air full of water vapor. And so let's fill this floor instead of with sand for vapor diffusion, let's put all this water on it. Well, what's going to happen? Even though we have a nice waterproof area all the way around here that's going to block air and block vapor diffusion, for air, it doesn't matter because it's all going to go and leak right through that drain. And so this was the big realization that we've kind of learned over time is you've got to let these assemblies dry to one direction. If you put too strong of a vapor retarder up, and then that air just leaks right on through, which we're accepting is just too hard to stop. Or if you get water from a leak or any other source inside the wall, you're going to have a problem. And the vapor retarder is now working against you, right? Now that vapor retarder is super wet inside. And now that vapor retarder is inhibiting the ability to dry out. And so we found, well, that's causing some problems. But hold on. Water vapor moves from high humidity to low humidity. So isn't that water vapor drying to the outside? Well, yes, historically it was. We had breathing paper, right? And it allowed water to release from the assembly, 5 perms or greater. But we had a lot of developments in technology since the 1950s, like plastic-based, foam plastic-based continuous exterior insulation. And what's this for? Vapor control? Not when it first came out. We have it addressed now. This was about comfort and cash, right? Energy code. So I remember back in the framing in the 90s in Arvada, a builder there wanted to build better code. They wanted to build a better house, good energy efficient house. And the early energy codes as well in 2000 had discussion about using continuous exterior insulation. And in this time, it was focused on replacing your wood structural sheathing, your 1/2 inch, OSB, if you will, wall sheathing on the outside, and just replacing that with a foam insulative sheathing, leaving enough OSB, wood structural panel, to brace the house structurally, but then replacing the rest of that with foam insulation. What are we thinking? Energy code, save money, let's be more comfortable. But how did we just change things without thinking about it? That's now no longer a breathing paper. That's not 5 perms open and dry and 30 perms wet. Now that's likely a class 1 or class 2 vapor retarder in terms of the permeability of this, conventional foam plastic sheathing. But we did that for energy code, but kind of forgetting, hold on, air might is leaking in here. It's a lot harder to do a good air barrier than it is to just put up a sheet of poly and block all that vapor diffusion. And what did we do now? We created a vapor sandwich, as they call it. Now we don't have either way to dry. We can't dry to the inside and we can't dry to the outside. And this was a big oops that kind of we were looking at in 2000, those early years of the I codes, where and this is part of that history where people will say, "Oh man, you can't put all these vapor retarders up. You can't make these homes airtight, right? Because I was at this house and the walls were rotting out." But why were the walls rotting out, right? Everyone has a different anecdotal story for why. And this is one of the stories that kind of led us to that. So this is where we're seeing a movement now in the vapor control to say, hey, if we don't really scrutinize the permeability of all this exterior stuff and all this exterior insulation we're putting on, continuous exterior, then we really need to drop down to a class 3 vapor retarder, like a paint, or utilize a responsive vapor retarder. So we can open drying up now towards the inside, since we may not be able to dry to the outside. Now, so unfortunately and sadly, I have hit my 1 o'clock moment. I have 13 slides left, but as we can see, the 13 slides will probably take me 5 to 10 minutes, upwards of that. I am not the host of this class. That is our Colorado Energy Department and Excel Energy and Erica. So I'm going to let her kind of let me know if I can wrap this out. For those of you that want to stay on the line and let me finish up, I'm here for you. But of course, this will still only be credited for 1 hour of education. Erica, sorry I didn't finish in time. How would you like to proceed?
Yeah, go ahead and wrap it up, Glenn. But for those of you who can't stay with us, appreciate you sticking on, and please take a moment to fill out that post-training survey.
All right. Thank you. Thank you. Thank you. I'll keep working at it, guys. The 60-minute stuff is tough for me, but I'll keep working at staying within that time and not feeling like I have to talk fast or rush through it. We'll definitely self-reflect when this is over. So thanks to those that stay on the line, because I enjoy this and I'm real excited to take you through, these last 13 slides I have prepared for you. So compliance for energy code. This is a slide I use in a lot of my energy code education, where I just like to point out, right? Just like buying thermal underwear. How thick is it? Are you using merino wool, or are you using something else? Or are you using cotton? Like, we as humans have a lot of choice in how we want to protect our bodies and stay comfortable when we're snowboarding. Well, the energy code gives us that same awesome ability to choose our way. How do we want to build the thermal envelope to protect our bodies just in the houses? And so the IECC and Chapter 11 of the IRC gives you essentially some prescriptive paths, right? Like the cookbook method. And you can utilize a U factor method for that, where you analyze the U value of all the different slices of materials in your assembly for their thermal transmission. Okay, that's a little more complicated. Maybe you want an easier recipe. Well, there's an R value recipe that disregards drywall and wood structural panel sheathing and just focuses you on the actual insulation materials. Put in this R value here and this R value here. Very, very simple recipe approach. And then, of course, there's this total UA approach, which allows you to go where you can trade off materials, more insulation here, less insulation here. So lots of different ways to even trade off the prescriptive recipe, just like a recipe might call for, butter, but you could also use margarine. Or how there's those substitutions in the recipes. That's kind of like your UA trade-off. You can trade things around and use substitutions. Then, of course, you could hire a chef to help you write your own recipe for your own food, if you will. I sometimes like to use that analogy as well, as you can tell. So you have the performance method, and this lets you scrutinize many more details of the house: orientation, solar shading, on and on and on. And now you can adapt and change your thermal envelope design based on other features that relate to energy loads on the house. And then, of course, we've now in 2015, we got the new energy rating index. And this picked up off of the HERS method that some of you may be familiar with, which was more of a market driven energy code program for like your Energy Star homes and for having for being able to satisfy the private market and how good your house energy performs. And now that's been embedded to where you can use that method for both the private market programs for showing how great your house is and for showing that it meets minimum energy code. So again, right, that's all about how you want to pick your thermal underwear. So if we look at this R value method, this is something that gets people confused a little bit. And it's definitely something those that stayed on the line, I'm excited to get through for you. The R value method. Prior to the 2021 IRC, the basic prescriptive recipe for thermal envelope requires continuous exterior insulation in these climate zones here, the colder climate zones. But we saw a big shift in 2021 that now brings down all of these climate zones, all looking for mandatory, required, prescriptive exterior continuous insulation. Now, you can also do an R30 cavity insulation. So there is a little caveat there for cavity insulation, but that either one of these kind of is a pretty big effect to changing how we've been building these homes, right? Continuous exterior insulation is not a historically conventional method, putting that over the top of our wood structural panel sheathing. So for energy code, prescriptive method, and remember, I showed you, you don't have to do this method. This is just the easy one design method. And it gives us here in these climate zones different combinations of cavity insulation with continuous 2x6, R20 in the cavity, R5 continuous, R13 with R10 continuous, etc. Also a complete exterior continuous insulation method that has no cavity insulation. So, okay, if we just start now throwing continuous exterior insulation up over the outside of these walls, is it a breathing paper? Does it allow drying to the outside? Well, that's a question for the designers to determine. And that's something for the third party authorities looking over that design to see, make sure it works, to check up on that as well. What are these materials you're putting on there? Because if you're still putting that class 1 vapor retarder on the inside or class 2 vapor retarder, you're going to be back to having that vapor sandwich as I discussed before. And you'll be rotting homes out the same way we were doing it in the 2000 code. So, all right, let's go then with a paint or a responsive vapor retarder. But the code knows, it also knows we're going to be getting air leakage in here. No matter how much we try to control this vapor, air is probably still going to find its way or moisture will find its way. So this is back to that. We got to dry. We got to have drying potential. But going down to a class 3 vapor retarder gives us great drying potential. That's good, but it also means more humidity is now being allowed into the wall. So we've increased the wetting potential, right? We're now making it more likely to get wet because we were trying to help it be able to dry. So the code's saying, hold on, we need to balance that a little bit. We need to try our best to eliminate that. So now in the vapor control code, for utilizing a class 3 vapor retarder, you've got to put a continuous exterior insulation. And you can see here how, actually, before we go back a slide, how there's that gradient of temperature through this wall, right? Really warm here and slowly getting colder and colder. And it's 40. So that means we're going to get liquid condensation because it's colder than our example dew point here. So the code says, all right, put continuous exterior insulation. And what does that mean? If you watch the slide, and I'll do my little clever magic here, right? It changed that gradient of temperature through our walls. Now, right now, that sheathing is kept a little bit more warm because we have a little more insulation on the outside than just our half-inch wood structural panel. So now we've been able to keep that sheathing a little bit warmer, and in standard normal conditions, the goal is to keep it above dew point temperature, not get that condensation. But in case it's an unusually cold day or unusual amount of humidity inside, oh, boom, we can still dry out even if we do get the condensation. So we're kind of getting both there, right? All right, vapor control. We got it solved. Okay. We've got the class 3 inside and we've got sufficient insulation on the outside. But now we decide I want to make a more thermally efficient home for the comfort and energy bills of that occupant, right? I already did vapor. Yay, checked the box. Now let's boost up our insulation and have a super thermally protective home. So we're going to go to 2x6 framing instead of 2x4. Great. Awesome for energy code. Bills will be lower. But what did we do now to that temperature gradient? Well, now we got to change that temperature gradient again because now we put more insulation on the warm side of that sheathing that we're trying to keep warm. And oops, now we have cold sheathing again. And now we're back to a higher potential of condensation to occur. So we got to go back and reevaluate our vapor control choices, right? It's like if you put on super thick thermal underwear that might be too thick to fit underneath your shell, your bib shell, your vapor control shell. So you got to reevaluate your that, right? Same, just for the analogy. So what are we going to do? We're going to put more continuous insulation on the outside. And then again, now we change that gradient of temperature through the entire assembly all the way out to the cold outside air. And we're back up again. Condensation goes away and we've kept that surface warm. So this is where for vapor control, I call it the battle of the dew point. Okay. So for vapor control, this side is the heat gain towards our sheathing that we're trying to keep warm and above dew point temperature. In energy code, you wouldn't call that heat gain. You would call that heat loss, and you would try to limit it as much as possible, right? But this is vapor control. So this is the side that we want that heat to come through to some degree to get to this point. And on the other side though, we have heat loss now. Oh, that sounds more familiar like energy code, right? The cold outside is pulling the heat out of our house and so we have to pay for more. Well, this heat loss is taking the heat away from this inside of the sheathing that we're trying to keep warm. And so for vapor control, these have to be balanced sufficiently that we maintain a temperature inside the assembly, not for our comfort, but for the building's comfort. Okay, so let's see how this works when we compare it to energy code and we're trying to actually do a design. So chapter 7, vapor control. This is a table you get for class 3 vapor retarders. And it tells us in climate zone 5, if you're going to have a 2x4 wall, you need R5 continuous over the outside. And if it's a 2x6 wall, well, now you got to go to more. You got to bump it up to that R7.5 on the outside. But what does this mean? 2x4 wall, 2x6 wall. Like everything I've been showing you has been referring to insulation, right? Blocking the heat from getting to where we want the heat to get to, the inside of our sheathing. So, this is where I'm a little critical of the code. I think there could be some adjustment in the future that might make this more understandable. This isn't worried about the air space inside the wall or like somehow the 2x6 stud has a different effect than a 2x4 stud. That's not what the science behind this is. What this is trying to say is it's assuming you're going to have R13 in the cavity of a 2x4 wall, and you're going to have R20 in the cavity of a 2x6 wall. And so it's saying, hey, if you have this much insulation, keeping the heat away from that surface, then you need a certain amount of insulation on the outside to try to retain whatever heat you do get on that surface. So that's an important thing to understand when you see this code refer to 2x4. It's focusing on what type of what maximum insulation that that would be designed inside there here, R13, R20, based on these cavity values here. So this is vapor control. All right, but now let's go look at energy for thermal comfort. Now it tells us R20 cavity with R5 continuous. And so this is where a lot of folks, especially in the public, they go, oh, this code is so stupid. It doesn't even make sense. What are these people doing? I mean, look at how dumb that is. It says R20 cavity with R5 continuous, but then for vapor, it's R20 cavity with R7.5 continuous. Who's writing this stupid code? No, you're forgetting. It's not one way that's the worst you can build and still be legal. You have a ton of choices for vapor control. You have a ton of choices for energy compliance, for thermal control. You have to make sure those two mesh, just like you got to make sure the thermal envelope, the thermal underwear meshes with the exterior bib, right? Up. Who's ready to go snowboarding? It's on my mind, as you can tell. Okay. So that's why this doesn't have to correlate there, because you could use this. Let's say you do an R, let's say you do this one for vapor control, an R7.5 continuous over a 2x6 wall, assuming an R20. So then maybe in your energy code compliance, you're going to use the performance method or a trade-off method, the UA trade-off res check, and you're going to raise that continuous to 7.5 so that you meet the continuous required for vapor control. Then that would allow you to lower that R20 cavity. And hey, that's not going to hurt your vapor control because you're putting less insulation on the side that we want the heat loss to the surface. So you just have to adapt your design so that both work. Okay. All right. So one more thing to mention into this, about 3 slides left here. You can also use, of course, spray foam insulation. There's all kinds of things in there that, again, I won't be able to flesh out for you completely in this last moment. Check out that on your own. But you can utilize spray foam insulation on the inside for vapor control. Talking about vapor control, this is allowed and it counts as continuous insulation. It does not count as continuous insulation when you're analyzing it for energy code, right? Because what? You have the studs that are thermal bridges cutting through that spray foam. So this is where there's another little thing to understand. Spray foam on the inside in between studs does count for your R value for, quote, continuous exterior insulation, but only for vapor. You can't look at it that way. This is a cavity insulation when you're looking at it for energy code. But what does this do for vapor control? This is an air impermeable insulation. And so that means that warm, humid air is not going to be able to touch the sheathing. And that's no longer our dew point, our condensing surface. Our condensing surface is now on the inside of the spray foam. And that's the surface we want to keep above 45 degrees. And we want to keep it warmer so that we don't get condensation. And so when you get to the vapor control stuff, you can do just spray foam on the inside to cover your vapor control, or you can do a combination of continuous exterior and spray foam on the inside just for vapor control. Now, when we're looking at this to say, okay, we have to balance out the vapor control that is keeping the heat at our condensing surface, the inside of the spray foam. Well, how do we equate that to the rest of the cavity that's blocking the heat from getting to it? Well, this is a 2x6 wall cavity. But do I have 2x6 worth of insulation blocking the heat from this condensing surface on the face of the spray foam? No, I don't. I really kind of have a 2x4 cavity possibly left here, right? And so that's where I say, looking at these things where they refer to the just the size of the studs doesn't really help us in really fully understanding the science behind all of this. Because in this example, for condensation control, even though this is a 2x6 wall, I could look here at this line and go, well, hold on. For R5 continuous, I can have the combination of both of these. That's going to keep the heat from leaving this surface and keep it warm. And then I need a 2x4 worth of insulation in the cavity, no more than that, because that's keeping the heat away. Well, even though it's 2x6 framing, I probably only have about a 2x4 cavity left. So just another little nuance, a deeper understanding I wanted to point out, and why I hope in the future we'll see this vapor control codes continue to get fine-tuned and really tell the story a little more clearly to us. So same thing if we look here right now, this is for our energy code stuff. Okay, so for vapor control, this spray foam is part of the R5 continuous for vapor control. But when we get to energy now, and we were to say, all right, for meeting thermal comfort of energy code, R13 cavity, R10 continuous. Now the spray foam is considered part of cavity insulation. And so you might not be able to make this one, or you might be able to make this value here, R20 cavity, combining both insulations and your exterior. So just important to remember that we can play around with these values just because the code gives us these easy R values to understand for energy code. For it doesn't have to correlate perfectly with vapor control, because energy code, we can do all of this over here. We can trade around all of this stuff. So one other final reminder for this: remember, your vapor control R values serve its function for its reason. This could be done for air sealing as well. Maybe you're doing this as part of your design to get some better air sealing. But then when you come and add additional cavity insulation, like air permeable on top of that, you can add both of these together to meet up your minimum R values for the whole assembly for energy code. And then just a reminder, definitely take a read when you use spray foam plastic. There's some other important things in here that I didn't explain to you, because I always want you to leave with more questions than answers. Hopefully you got a few answers out of this, and hopefully you leave with some things that you're curious about, and you'll go continue learning on your own. Sorry for having a little bit longer time here. I'm talking a little faster than I wanted, but I hope you guys all did enjoy the presentation. Thanks so much.
Thanks, Glenn. I appreciate it. We will stay on the line for another minute or two. If any questions do come in, you can write your question in the chat, the Q&A, or you can even raise your hand. So
Zoom go. Oh, there it is. Stop
um,
sharing. Okay.
and I am also one of those dorky skiers, so
That's a tease, honey. I'm a snow skater now. So technically I do have two planks. I have my upper deck and the lower deck. So I'm a two
oh,
planker
whoa.
guy.
That's different. Yeah.
Hey,
Well, you're getting a lot of thanks in the chat. I'm gonna go ahead and stop the recording.